Hello everyone, this is Dr. Zach. For today's lesson, you are going to calculate the volume of a storage shed using Simpson's method. That will be part A. For part B, notice that you're going to be looking for the equation of your two line segments. Then you will use integration to find the volume of the shed. Once you've completed that, determine the difference in the actual volume versus the approximate volume. At this point, you should have completed practicing Simpson's method and writing the volume equation. Did you notice that the difference between your actual and your approximate was 0 feet cubed? Now, I'd like you to think about the shape of this shed and how Simpson's method is actually working. If Simpson's method is using curves in order to approximate, and those curves are second-degree polynomials, the error that occurs when you are looking at lines might make more sense. All right, so thinking about Simpson's rule, did you remember that there's a lovely pattern happening? You have your delta x multiplied by your integrating factor of 1/3. Then you have the function at the a value, and lovely pattern 4, 2, 4. This pattern continues, ends in a 4, and then you'll have the last point on the interval for which you are integrating. How good is that answer? So if we're looking for errors in the trapezoidal rule or Simpson's rule, we actually have some formulas to work with. The error, which we're going to call E, is going to be less than or equal to b minus a, those are your endpoints. It's going to be cubed over 12n squared, and then the maximum value of your second derivative on the interval ab. Okay, so that is how we're going to figure out the error for any problem that has a trapezoidal rule being used. Now, Simpson's rule has a different error. The error is less than or equal to, now this one is b minus a over 180. Here's your n to the fourth. So the more n values, the less error you're going to have. Your b minus a is raised to the fifth power. Then we'll multiply by the maximum of the fourth derivative on the interval a, b again. All right, so that seems rather complex. We are going to figure out where the formulas came from many lessons from now, but for today's work, let's just check and use those formulas. All right, so for example 1, we're going to estimate the errors in approximating our integral with n equals 4. Let's consider our error formula. Your error is always going to be less than or equal to your b minus a, so that's 3 minus 1 to the fifth power divided by 180. In this case, we used 4 partitions, so 4 to the fourth power. Then I want the maximum value of the fourth derivative on the interval from 1 to 3. So I need to find the fourth derivative. F of x is your 2x cubed. F prime of x, let's find that derivative. We're going to have 6x squared. F double prime x is going to be 12x. And the third derivative is 12. And then the fourth derivative of x is 0. So on the interval 1, 3, the largest value of the derivative is 0. So we take this, we multiply it by 0. That tells us that the error is going to be less than or equal to 0. So if I use Simpson's method for 2x to the third power, then my error will be less than or equal to 0. There will be no error at all. Think about y for a minute. Think about how parabolic curves could be used to hug a third-degree polynomial. For our second example, we're looking at the problem in a different way. We want to find the n value such that the error in our approximation for a definite integral is always less than or equal to 0.00001, given this function. Okay, so let's think about one more time what that error should be. So the error is less than or equal to your b minus a raised to the 5th power divided by 180 n, which we don't know what that is, to the 4th power times the maximum of the 4th derivative on AB. AB in this case is going to be from 0 to 1. So let's start by finding the 4th derivative. Rewrite your f of x to be equal to 1 plus x to the negative 1. Find your derivative. F prime of x is going to be negative 1. 1 plus x to the negative 2. F double prime x is going to be 2, 1 plus x to the negative 3. F triple prime x is going to be your negative 6. Notice we've got a Fibonacci sequence happening here as our coefficients. And then our 4th derivative is going to be positive 24, 1 plus x to the negative 5. Now remember, we want the maximum value of the derivative on 0, 1. Let's consider the endpoints. If I put 0, the 4th derivative at 0 is going to be 24. And if I put in 1, the 4th derivative is going to be, isn't that going to be smaller than 24? And let's go with 24 is the max. All right, so now what do we know? We know that the absolute value of the error is going to be less than or equal to our b minus a, which is 1, to the 5th power over 180. I still don't know the n value, so I keep n to the 4th multiplied by 24. Keep in mind, the goal of the problem is to keep our error smaller than 10 to the negative 5th power. So what do we know? We know that 24 over 180 n to the 4th has to be less than or equal to 10 to the negative 5th power. Let's solve for n to the 4th. We have cross multiplication, which is permitted since n is a positive number. It's going to be greater. We have 24 over 180, that was 180. And times 10 to the 5th power. We'll now take the 4th root of both sides. Once again, this is a positive answer, so we will not have to worry about plus or minus. And we know that n is going to be greater than or equal to our 10.74. All right, so in order for this error to be less than 10 to the negative 5th power, the n has to be greater than 10.74. But think about Simpson's method for a moment. Simpson's method, you have to use an even n value. I'd like to use 10, but that's not permitted because 10 is not going to be the right number so that it is larger than 10.74. So in order to get the error where we want, the n value that we have to have, or the number of partitions, needs to be 12. At this point, you might be asking yourself, am I expected to memorize the error formula? And the answer to that is no. I do not want you to memorize. The purpose of this lesson is I want you to be aware that when you do numerical integration, error will occur. And sometimes we need to figure out how much error is going to occur for our problems. For example 3, though, we have this complex integral. Doesn't it look like fun? We don't know how to integrate that problem. And it gives the circumference of an ellipse. We're going to use Simpson's rule with n equals 8 to approximate this circumference. We're not even going to think about the error. We're just, once again, going to use Simpson's rule. So our delta x in this problem is going to be pi over 2 divided by 8, which gives us a pi over 16 as delta x. I'm going to let f of x equal what's inside my integral. So I've got the square root of 1 plus 2/3 sine squared theta as f of x. So So the circumference is going to be your delta x, which is pi over 16, times your multiplier, which in this problem is 1/3. And then we will have our first value, which will be f at 0, follow through with incremental increases of pi over 16. And we're going to continue these until we get to 8 pi over 16. So go ahead, write all of these parts out. Remember, when you take your AP exam, it's important to show what you are adding or what you are calculating, even if you are using a calculator to come up with the values. So use function notation so that you write less. However, it is important to show what you are actually adding when you work out a Riemann sum, when you work out a trapezoidal rule, or even when you work out a Simpson's method problem. Remember, your last term should be the multiplier 1, and the term before that should end with the multiplier of 4. And now we have f at 8 pi over 16. Take your answer though, because the circumference is not quite right. Remember, this 8√3 also needs to be completed. So once we have the 8 times the square root of 3 written on the problem, then you can find your final solution, which is approximately 21.347.